Well, this morning I want to take up the exact distribution for simultaneous equation estimators, and the simplest case of all being the two-stage least squares or instrumental variable type of estimator. And the only case that this is really now known about, where the distribution is now researched, is the ordinary classical model where we have the usual assumptions of normally distributed errors and non-stochastic exogenous variables. In fact, the only thing that I'm going to attempt in these lectures is the discussion of the two endogenous variable case. That is the case where the equation to be estimated contains only two endogenous variables. And even there, the only distribution that has really been considered is the distribution of the other endogenous variable, assuming that the coefficient of one endogenous variable is standardized. Early work in this field started with an article by Richardson in JASA 1968, although earlier Baseman had looked at some special cases where the number of exogenous variables was 2 or 3. What I want to do is, first of all, to set up the model in a general kind of way to show how one normally transforms the model to obtain a rather simplified discussion by linearly transforming the exogenous variables, and then to explain how the problem is related to some problems in the statistics of non-central Wishart distributions. But then this will all be done with a general kind of k endogenous variable kind of background, but then rather rapidly move down to the two endogenous variable case again to actually derive the distribution. I'm afraid also I shall be a bit what should I say, idiosyncratic in my treatment, because I shall use my own treatment as originally put forward in an article in Econometric in 1971, rather than the Richardson treatment, partly because the Richardson treatment requires more knowledge of the distribution of non-central chi-squareds, whereas my own treatment starts with simple central chi-squareds as the background. Partly because I use the same treatment later for the k endogenous variable case in my 1976 Econometric article, and I think that definitely does give an easier approach to the k endogenous variable problem than the one which is used by Anderson and Peter Phillips. So let's look at the model that we're estimating using my own kind of notation, I'm afraid. We have a model that can be written in the form Now, ignore the presence of the stars for the moment. The only reason for putting stars on these variables is that later on I'm going to transform them linearly to other variables, and it's at that stage convenient to have non-starred variables for the transformed variables. So these are the original variables of the model. Here we have a k by k square matrix. The y star t are the endogenous variables. C is a k by h matrix of coefficients of the exogenous variables, which are the z star t. Z star t then is an h by 1 vector of non-stochastic exogenous variables. U star t is the k by 1 vector of normally distributed errors. And of course we have a general variance matrix for the individual U star t, but we also have serial independence, U star t independent of U star s. Straightforward set of assumptions. We then take one particular equation, the first equation, and we're going to discuss the estimates of the first equation in the system. I'll write it in the form at this stage. The extra suffix 1 means that we're taking the variables in the model which occur in the first equation with non-zero coefficients, or with coefficients not constrained to be 0. And then, in addition, we introduce a standard notation for the whole set of data. And I'm going to introduce a 0 restriction so that we write the y1t in the form y1 star t in the form y1 star. Sorry. Yes, we write it in the form, first of all, y1 itself. Sorry, without the suffix t, is a t by 1 vector of the endogenous variable whose coefficient is constrained to be -1. y1 star primed, sorry, y1 star itself is the remaining unconstrained coefficient endogenous variables in the first equation. And so if we now put the two together, that is the matrix of data for the y1 star t variables. The tth column of this combined matrix is y1 star t prime. Then similarly, we write z1 star for the data matrix corresponding to the z1 star t. And so we can write the whole set of equations in the form minus y1 Yes, I think that's okay. So, okay, my B1, yes, I've got a change here. I should have had a star on here initially. so that my B1 star is minus 1 B1. So then substituting the following, that x1 star yes, I'm sorry, I star missing here too. Now substituting x1 star equals y1 star z1 star, putting the two lots of variables together in one matrix and calling it x1 star, then we can write the estimation equation, the instrumental variable estimator. Well, again, I want to introduce arbitrary instrumental variables. I'll discuss the choice of the instrumental variables later, but at the moment, in order to differentiate them from what we have here, the z1 star, the variables, exogenous variables occurring in the first equation, I'm going to rather arbitrarily introduce a suffix z4. So let's now refer to our instrumental variables that we're going to use as z4. In this kind of work, what one normally does is to assume that z4 includes the z1 star, so that included in the z star 4 variables are the z1 star variables, and then in addition to that we have some selection of the other exogenous variables in the model. Furthermore, we can always introduce arbitrary instrumental variables into the set Z4 by introducing these variables into the reduced form of the model with zero coefficients. So at no stage am I going to assume that the Z4 variables have non-zero coefficients in the reduced form equations of the model, and that gives us a simple technique for introducing arbitrary instrumental variables into our set of instrumental variables. We'll see how that works out later. But at the moment we can simply say that Z4 star can consist of any set of non-stochastic variables with the usual property then of course being independent of the U1 star. Sorry, my U1 contains a star. Well, then I take it that we're familiar with the usual form of instrumental variable estimation equation. Well, again, we need still stars on everything. And one can either work with this form of equation, or one can alternatively work with the errors in the IV estimates. That one gets by simply substituting what y1 star is from equation 1 into here, and then in the usual way one can take everything over to the other side, and if I can simply say repeat what we have in large square brackets here, and then multiply this by, and we now have the errors b1 hat star minus b1 star, c1 hat star minus c1 star, and then on the other side the only change is that we replace the y1 star by the u1 star. And in the standard discussion, that has the effect that since the u1 star is a completely random variable, it doesn't, like the y1 star, have a non-stochastic part. One finds oneself dealing with a kind of central chi-squared type of variable rather than a non-central type chi-squared type of variable. And that slightly simplifies some of the formulae to work with this equation. In fact, this latter equation is the form that I shall be working with myself. The previous form is more like the one used by Anderson. Well, in any case, the next stage is the same, whichever equation you deal with, and that is to set up a linear transformation of the z's on the assumption, which is often true in this kind of literature, that one is interested in discussing the joint distribution of the B1 star rather than the C1 star. Now, in a sense, if one's prepared to deal with the joint distribution of the B1 star with k of any order, then the distinction between the B1 star and the C1 star can be abandoned to some extent by noticing that you can think of the Z1s as being a simplified version of the endogenous variables, where the variance of the reduced form errors is actually put equal to 0. So that if you look at the joint distribution of the B1 star, you can easily get the additional joint distribution of both B1 star and C1 star by considering what happens to your joint distribution as some of the variances in the reduced form equations become 0. And that's very often a convenient way of doing things, so that I shall concentrate upon the distribution of the B1 star and let me now present this transformation. We introduce a transformation from Z to Z star, or rather Z star to Z, using a matrix of a square matrix H, which is obviously, I notice that I'm using H here, but I've also got the dimensions are actually equal to capital H as well. This won't worry us because I'm immediately going to specialize the form of the H matrix. So that it has suffixes on it, if you see what I mean. Now the point is that we're, at this point, splitting the Z star up into, first of all, the Z1 star, which occur in the first equation, Z2 star, which occur in Z4 star, but not in Z1 star, and finally Z3 star, which don't occur in Z4 star, but occur in the model determining the y's. In other words, I'm now assuming that Z1 star and the rest give the usual partition between those Z star variables which occur in the first equation and those which don't. But then I'm assuming that Z4 star is simply being defined as obtained by taking Z1 star and Z2 star. So the Z3 star are the variables that are not being used as instrumental variables. As I say, if you want to use arbitrary instrumental variables, then you can add them to the set Z star before making this division into Z4 star and Z3 star, before dividing the Z star into Z4 star and Z3 star. Clear why I'm using Z4 star at this stage. It's more convenient to have the partition into three sets and then define Z4 stars, the combination of two of these sets. Well, now we choose the transformation so that we have the following properties. Again, this is slightly non-standard on my part. The usual thing to do is to choose the transformation so that we have Z prime Z equals I, an obvious kind of standardization. But that has some disadvantages when you consider the asymptotic properties of the estimators and the way that one can derive the asymptotic properties of the estimators as t goes to infinity. And so I myself prefer to make the assumption that Z prime Z divided by t equals I, or alternatively the variance matrix, or the second moment matrix of the Z prime Z is the unit matrix. Furthermore, since we're not particularly interested in the coefficients of C1 star, C1 star hat coefficients, we make the further requirement that Z1 star upon T equals I, and that Z4 star prime Z4 star upon T equals I. Now you can see how this can be done. Essentially what we're doing is to take a set of vectors, the Z vectors, Z star vectors, and orthonormalize them, but in effect we're going to choose the transformation so that first of all we orthonormalize the Z1 star to each other. We set them so that their product matrix is the unit matrix. Then we take the Z4 star by adding the extra set of Z2 star variables and orthonormalize them both to Z1 star and to themselves, which intuitively one can always do. One can always, first of all, choose the Z2 star so that the new transform variables Z2 are independent of the Z1 star variables, orthogonal to the Z1 star variables, and then do a supplementary transformation to get them orthogonal to each other. And then finally, we redefine the Z3 variables so that they're linear combinations of all the Z star variables, orthogonal to both all the Z4 variables, the new Z4 variables, and then orthogonal to each other. So intuitively it's always possible to make this kind of transformation, and in fact you can, for example, also require that all the H's are upper triangular matrices. That would be a standard way of carrying through such an orthogonalization. And if you make that further restriction, what you're doing, you see, is to say that you require that the H matrix satisfies H primed, Z star primed, Z star upon T times H equals I, or you're probably familiar with the fact that that is then equivalent to that H primed equals Z star primed Z star upon T inverse. And we're familiar with the idea that a positive definite matrix, such as we have on the right-hand side here, can always be factored into a product of this type with H upper triangular. And that's the simplest way of getting this required transformation. So, having done this, where does it get us? Well, let's discuss this on its own. We later are going to do a kind of similar transformation on the x1 star. But all that's going to happen here, you see, is that if you consider Z4 star primed, Z4 star, Z4 star inverse into Z4 star. What we're going to have is that the if you consider what I'll call Z4 prime Z4 prime Z4 minus 1 Z4, this is going to be obtained by transforming my Z4 star by the, yes, I ought to have written this up separately. Let me write it up separately. Z4 star times H1, H2, H3, 0 will be equal to Z4. Just partitioning, taking the first two blocks of columns of this equation here. Now if you substitute what Z4 star is in terms of Z4 star, into this equation here, you will immediately see that the H transformation matrices cancel, and so that these two expressions are equal to each other. So, in either of these equations that I've written down, I can simply say that I can take out the stars on the Z4 stars. Convenient for me, I suppose you'll have to rewrite the whole thing. The same here, of course. What we now can introduce is a convenient notation. And it's convenient, I think, to introduce some kind of notation like x1 prime z4 upon t is equal to q. Let's see, x1 star prime z4 upon t equals q. And then partition q equals q1 q2. Yep. Where no, I'm sorry. I'm missing out some details here, but of course what I want to do is to split Z4 up into Z1, Z2, and so write this in the form Q1, Q2, where Q1 is then by definition equals X1 star found yes, I was right first time. I'm sorry. I was right first time. Very sorry. That should be Q1, Q2. Because I'm now wanting to distinguish between X1 star equals Y1 star, Z1 star, and so Q1 is going to be Y1 star prime Z4 upon T. Q2 is going to be Z1 star prime Z4 upon T. Then the other thing one notices, you see, is that if you divide all these equations by T, 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 then Z4 prime Z4 upon T is just the unit matrix, and so you can cancel that out. Finally, introduce the further notation. Well, I think it's probably better to turn this round so that it's not actually the same way round as we had before. Call that little q. Now that's very similar to my definition that I have here, the x1 star prime z4 upon t. The only thing is that I usually prefer myself to work with column vectors. This is just a vector, so I've turned it round, transposed it, compared with this definition of my capital Q to make it a column vector. Well, then I think you can see that my first block of equations, which in fact I've just rubbed out to make room, takes the form Q prime into B1 hat minus B1 C1 hat minus C1 is equal to Q times little q. Again, we need stars on all these elements here.
Deviation form, should little q have u star instead of y star?
Or you change the vector on the left-hand side of the equation?
Yes, one can either deal with the first block of equations or the second block of equations in much the same way. And actually, I'm looking at the first block of equations, which have got the y ones. Oh, I'm sorry. Yes, of course. I'm doing it inconsistently. Yes, I'm doing it inconsistently. If I want to have the deviation form, then I've got to have the u star here. If I'm looking at the original estimates, then I define q the way I've done it. Yes, I'm sorry. Now, of course, what we can do is to split these equations up using the form of the Q1 and the Q2. In fact, we notice that Q yes. I'm sorry, I have made a rather stupid slip here. I was very uncertain which way I should split things here. And what I need to do actually is to notice the following about my Q. That is that we can write it in the form y1 star primed z1 star upon t y1 yes, no star on the z1, y1 star primed z2 upon t. Yes, I have this too late in my note. Then we have z1 primed z1 upon t, z1 primed z2 upon t. Now at this stage I ought to be saying, okay, I'm transforming the z1 star variables by using the h1 transformation. Essentially this h1 is being applied to the Z1 star variables to define variable Z1. If we split the Z matrix up into Z1, Z2, Z3, using the same number of columns in each case as we used to define Z1 star, Z2, Z3. Now it's obviously convenient to use the inverse transformation on C1 hat. That means that it's convenient to define C1 hat without a star to be equal to H1 minus 1 times C1 hat star. Sorry. Yes, that's right. H1 Z1 hat star. Now, since it's such a reciprocal transformation of the coefficients and the variables would leave the form of the equation, structural equation, unchanged, we can make such a transformation here so that we now define the Q in terms of the x1 star. It's convenient, perhaps temporarily, to write that x1 is equal to my previous y1 star, but now my transform z1. And the effect of this is going to be that if I define my q, redefine my q in terms of the transformed variables, that we shall still have a y1 star here, but we shall have a z1 in place of z1 star, defining the lower block of rows. Well, now the advantage of that is that clearly from the definition, z1 prime z1 upon t becomes a unit matrix, and the z1 prime z2 upon t becomes a zero matrix because we've orthogonalized the z1 and the z2 variables. And now I must admit that this whole business of splitting up my Q's into Q1 and Q2 was a mistake, because I hadn't actually presented this step of the argument yet. And what I really want to do is to define my Q matrix to be Q1, Q2, I0 as the definition of the Q1 and Q2. And now this equation, because I've redefined my C1 star, should have a C1 hat there. Remember, I redefined my C1 star at this stage as the coefficients of the first equation that would be applied to the transformed Z's, Z1. Now, okay, what we're now going to do is to write down the set of equations here explicitly in terms of the partition of the Q matrix into this form here, and correspondingly we are going to define Q, little q, to be Q1, Q2, where this Q1 is a vector of the same number of rows, elements as Q1 has rows. In other words, the same number of elements as the number of exogenous variables in the equation we're studying. Q2 is the remainder of that vector. We then see that we can write down the equations in the form, well, first of all, let's write down Q prime. And of course that's going to be Q1 prime plus Q2 prime and then Q1 and then I. From that it follows fairly easily that we can now write down the block of equations in the form the first block of equations. The second block of equations is the following. So, skipped one stage in my notes. Now one eliminates C1 hat by multiplying by Q1 and subtracting, and so ends up with a somewhat simpler form. I'm sorry, Q2 prime, Q2 prime, little q2. Or alternatively, we have the equation that B1 hat star is equal to Q2 prime inverse Q2 little q2. So now what we have to do is to look at our Q2s, see what their properties are, and in fact we see that if you look at any column of this matrix, any column of Q2, which is capital Q2, which is turning up here, that column is normally distributed. The elements are jointly normally distributed. Furthermore, because of the way that we've normalized or orthonormalized our instrumental variables, each column is independent of every other column. So we have a set of independent, jointly normally distributed vectors. Each column is such a vector. If we looked at any element of Q2, Q2 prime, we would see that it was a covariance between a sample covariance between such vectors. If we had the case that the mean of these normally distributed variables were all 0, Q2, Q2 prime would be of the nature of a Wishart matrix. Because we don't have that property, because the means of these normally distributed variables are non-zero, we find that what we have here is a non-central Wishart matrix. And that is what makes this problem complicated. Let me now fill in again the algebra of what I was just stating. Let us have a look at any element of the Q2 matrix and take any particular column. Then, since by definition Q2 is equal to Y1 star Y1 star primed Z2 upon T. If we take any one column, what we're looking at is one of these Z2 variables, say column I. If we look at, I'll just label Q2I as the ith column. Then what we have is an expression of the form sigma Y1 star T primed Z I T divided by T. Since the Z's are non-stochastic, the Y1 stars are linear combination of the Z's, and the error on the reduced form equation, which is a normally distributed variable. So what we have here is a variable which is a vector, because I've kept the Y1 star T as a vector of different endogenous variables. And we see that the such a combination is normally distributed, but with a non-zero mean, so that we have a vector here of variables with non-zero means. We also see, however, that because if you consider any two such columns, you're multiplying up by the ZIT in fact determining the covariance between the variables in the two columns, but the ZIT themselves are orthogonal. So we get this kind of result, which one can fairly easily work out by just substituting in what the reduced form is for the Y1 star. Let us, in fact, look at, to make it easily manipulable. The y1 star, jth element in the y1 star, z1 zit over t, and we will have to substitute in from the reduced form, and so what I will do is to write down the reduced form which is involved here, and I see in fact that I've got to the end of my hour, and that perhaps I'd better leave this algebra until next week. But the essential idea, which I was just wanting to put over before I got into that algebra, is the idea that the columns of the Q2 are all independent of each other. They are all normally distributed, so that what one has here is an inverse of a Wishart matrix, but unfortunately a non-central Wishart matrix, and that similarly one consider this column Q2, capital Q2, small q2, as being also a similar kind of column extracted from a Wishart matrix, and that one then has to think about the joint distribution of the elements of these Wishart matrices, and clearly the problem is rather difficult. A great simplification occurs in the two endogenous variable case, because in that case both our matrix and our vector are actually one-dimensional, and so all we've got is a ratio of two scalars. And so when we get to that case, all we've got to do is to look at the distribution of the two scalars, and then derive from that joint distribution the distribution of the ratio. And that is really what I'm going to do next time. As I say, I'll finish this off by looking at the general case again to explain what the actual distributions are of the elements of Q2 in the general model, so that we can see how this thing is at least originally set up in the K endogenous variable case. Well, so that's the end of this general discussion. Are there any questions?
Just to show, has there been any advances when these Zs are not fixed? Because in practice it's rarely the case that they are simultaneous systems.
Well, there are practically no exact distribution, theory of the exact distribution of these distribution functions for any non-classical case. Only the very simplest kind of autoregressive coefficient case, which is, not this simultaneous equation problem, but for the simple OLS estimates for autoregressive models, even for the simplest cases there, it's still difficult to derive the exact distributions. So as soon as you move out of the kind of static econometric model, you find there's hardly any exact theory available. I think I agree with you. That's very unfortunate. It means that most of this is not very realistic for actual econometric estimation, except perhaps, for example, well, one possibility in discussing panel data problems is, in that case, you see, what you've got is that each member of the panel, each member of the cross-section is independent of any other member, and you can set this kind of thing up for, again, simple models, very simple models, so that you can get some exact results from that case, which really depend upon the idea of the independence in the cross-section and using that. Okay.
This is your transformation to doing your orthonormal.
Yes, that's right.
Now, on the board, you actually wrote that Z1 stars is a star on TSY. Now, surely those stars should be just disappearing on these.
Yes, that's right.
We should have the stars on there.
That's right.
Yes, okay. So when
You're
when
orthonormalizing